So the goal here is to find the density of a cube with proper uncertainty attached to it and rounded to the proper number of significant digits. So let's imagine that we have a cube here, looks like this. It's a pretty strange looking cube, but close enough. And someone comes and they measure off the various sides with associated uncertainty. So 3.20 plus or minus 0.05 centimeters. Again, this value is half the last readable digit, so half a millimeter is the uncertainty on each of those measurements. This is an estimated digit. Okay. All right, and then we also have the mass of this object as weighed on a digital scale. Because the scale is digital, the uncertainty is equal to the last readable digit. Okay, so these values are all correctly written down. So what we'll do first is we will solve for what is the percent uncertainty that each of these values have. Since to get the volume, we need to multiply them all together. That will have us add up the percent uncertainties, and that will be the percentage uncertainty on the volume. Okay, so we've converted these into into relative uncertainties displayed as a percent. Something to note is that the larger the value, okay, from an analog measure, the larger the value, the lower the amount of relative uncertainty that you have, okay? This has implications for later, especially when we're measuring something over a length of time. It's always better to take a longer length of time if, say, you're looking at like oscillations of something, or say like reflections of a pulse in a spring. It's better to allow that to go back and forth numerous times to lower the percent uncertainty in your reading, okay? Because this is inherent in the tool, and the longer the distance you can measure over, the less the overall relative uncertainty is that you'll have, okay? So that's good. Now what we'll do is we'll go through and we'll multiply this out to find what the volume value is, okay? And then we'll go right through and do the density, and we'll see what we do with all of these uncertainties. So we'll find the volume first. Okay, so multiplying these together, you get 32.56352 centimeters cubed. We'll just leave this for now because we're going for density. We don't really care about the uncertainty on the total uncertainty on the cube, because we're going to add it all up at the end anyway. Okay, so density is mass per unit volume. All right, so the mass that we calculated here, 201.7 plus or minus 0.1 gram divided by 32.56352. And here, let's just get rid of this because we'll deal with that after. So we'll find the value that we get for our density, and we'll leave on all the sig figs for now. Okay, so I said leave on all the sig figs. I just meant leave on all the digits. All right, some of these are not significant, but they still go into the overall density calculation. So you get this, 6.194,047,818 cubic centimeters. Now clearly we can't access digits that are this far down, right? We're going into tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionth, etc., etc., etc. We cannot get that precise, so we have to round this value off. Before we do, though, we want to know what our total uncertainty is. So before we do that, we need to calculate the percent uncertainty on our mass, okay? And let's just make sure we have the right units too. So that's grams over cubic centimeters, so grams per cubic centimeter. So this was plus or minus 0.1 grams, so we go 0.1 grams divided by 201.7 grams times 100. So we're not really getting a whole lot of contribution here from that value. All right, so now the total percentage uncertainty on this is the sum of all the uncertainties that went into this value. Since we're multiplying and dividing the whole time, we're just going to add our percentage uncertainties up to get the total uncertainty. So we get plus or minus 4.739 percent grams per cubic centimeter. So now we have to do our rounding. So looking at our values, this has 4 significant digits here. These all have 3 significant digits. Since we did all multiplying and dividing, we can only show in our final value 3 significant digits. Even though this has 4, the 3 significant digits has less significant digits, so that's the rounding that we have to go to. So we look at this value here, okay, and we see that it just is a 4, so we get 6.19 plus or minus 4.74% grams per cubic centimeter, and then usually what you'll do is you'll convert that out to an absolute value. So to do that, use this value, multiply by the 4.739% to get it back into the units of grams per cubic centimeter and away from percent. So at the end of the day, you would get this, 6.19 plus or minus 0.29, and you get a whole bunch of digits there, 5, 3, 5, 9, 2, 6, 1. But it would not make sense to show more precision than this value here. So we're going to round to that decimal place, so that'll be there. So 6.19 plus or minus 0.29 grams per cubic centimeter. Okay, so there is like the full process of calculating a density and propagating your uncertainty through your measurements. And this would be your final answer. 3 sig figs, your uncertainty shown to the same precision as the value over here. We think this is the iron. And we can find that iron should have a density of 7.9, let's just see here, 7.874. So what we want to do now is an error analysis. Okay, so an error analysis is just going to compare what we got to what we should have got and see if the difference can be accounted for by uncertainty in our original measurements. All right, so we're going to go actual minus experimental divided by actual, absolute value of that times 100. Okay, so actual 7.874, this is the accepted value, 6.19 divided by 7.874. This is all grams per cubic centimeter. Let's see what we get. Okay, so the error that this gives us is 21.4% error. Okay, so our error is 21.4%. Our allowable uncertainty is 4.74%. Okay, so 21.4 minus 4.74, this is from the tools that we used. All right, so this difference cannot be accounted for by just simple random uncertainty in our measurements. So basically something is wrong with the experiment that we did. So we cannot account for about 16% of that error. So where does it come from? Where do you think this came from? What's the issue here? What would you suspect the issue is? Why did this happen? This is what you have to answer, okay? So we got that this thing was less dense than it should have been, okay? Less dense than it should have been. If we're getting less dense than it should have been, either our mass was low or our volume measured high. Okay, right? If we're getting a density that's lower than we should, it must mean that we measured our mass too low or our volume too high, or a combination of both. What's an explanation for that? How could something like that have happened? So when you look at the cube, I'm not sure what you did with your cube, but one thing you might have noticed with your cube is it has a hole in the top or it has a hook in there. If it has a hook, that hook is made of brass, so it's made of a different material. Or if you took the hook out, you left a hole in there, right? If you left a hole, that's going to give you a lower mass than you should have got. Okay, so that's one maybe possibility. So going back to look at your numbers, seeing what they say, and trying to explain out why you would get a value that was off by a significant amount, right? If it was off but it was within 4%, we would say, or sorry, about 5%, we would say, well, that's just measurement uncertainty, that we didn't do anything wrong. There's no systematic error in our measurements. It's just off because our tools can only give us so much precision, right? This one is off by a large enough amount that we have to go back and identify what happened, right? So that might be one explanation. There's a hole inside here. You're not getting the mass from the hole. I'm not sure if that's enough to account for how far off we were, but that's maybe a start. Any other ideas? What else could have happened? Maybe a zero error? What's a zero error? Yeah, exactly. It's like if someone came to the scale before you and tared it with something on it, and then you came back and didn't re-tear it to zero, it might start off with a negative reading. Or it's possible that it could have started off with a positive reading. So maybe you forgot to zero the scale. That's a possibility. Sometimes the cubes get dropped and their corners are rounded off, right? So if you have a rounded off corner, that can mess with your measurements, right? It shouldn't reduce the amount of mass because it's not like chunks of mass went missing, they just got dented. But it is possible that it messes with your measurement values that you're reading off of there. So part of doing an experiment like this is if you are off, trying to explain why you're off and how you would fix it next time. All right, so we'll get into that next class.